Welcome again, Physics 100 students. And hopefully you did well in the last exam. Although since I wrote and video recording this 6 months before the start of the class, well actually 6 months before this portion of the class, I'm only guessing at this point that you did well. The following half of the class is, for the most part, a significant difference than the first half of the class. There's a big divide between the two sections. So if you started on the first half, there's still a chance for you to do well in the second half. For those not in my Physics 100 class, if you're in a different class that is usually a 2-semester class, after this lecture, you will be doing material and looking at material for the second semester of your 2-semester course. This one usually comes in the first semester. This chapter is going to be the most difficult chapter for the next midterm. After that, it gets pretty straightforward for most of the rest of the semester, at least for what we do in this class. Our goal for this particular lecture is to understand liquids and gases and fluids in general. Our objectives are to understand pressure, what it is, what it does. We're going to understand buoyancy and how to calculate buoyancy. We're trying to understand Archimedes' principle, which allows you to get densities of objects, and we'll learn about how pressure is affected when a fluid moves, particularly when fluids like water move. Pressure. So what is pressure? Well, imagine the molecules of air in this room moving around. And well, of course they move in straight lines. And some particle of air is moving towards me, and it runs into me and bounces off of me at probably the same speed it hit me. Now, when an object collides with you, that's what type of problem? So what type of problem is a collision problem? That is a momentum problem. So now we have a momentum problem. Mass times velocity. The gas hitting me, bouncing off me, and so we take mass times delta v, which is the impulse imparted on the air by me, and I get an equal the opposite impulse in the other direction, minus m delta v. Now, since it's changing direction, that delta v is very large. And m delta v is also equal to force times time. So the air hitting me and bouncing off imparts a force onto me. This force is proportional to area, because the bigger the area, the more air that hits you. And so pressure is merely the force per area that a fluid exerts on everything around it, because all that material is running into everything. So force equals pressure times area. There's a few things that create pressure and determine the value of that pressure. In an atmosphere where you don't have enclosed air, it's determined by gravity, so it's the weight of the stuff above you. If something's enclosed, like in a tire, then it's the density of air, how much air you have in there, and the temperature of the air, which determines the pressure. So on Earth, for every square inch of the surface of the Earth, there lies above it 14 pounds of air. Now, air doesn't weigh a whole lot, but 100 miles of air weigh about 14 pounds. So that means that every inch of my body is being pushed inwards by the air around me by 14 pounds per square inch. And there's a lot of square inches of me. And so that's a lot of force inwards. So the question is, why am I not crushed by this intense, insane pressure? Well, we have to think about net forces here, as usual. Think of a door. We have two sides to the door. Imagine that we have air pushing one side of the door outwards. Well, if that was the only part of the picture, the door would fly open. But suppose now air is pushing on the other side of the door, and so you have forces on both sides of the door, because you have pressures on both sides of the door. I have an internal pressure that pushes outwards, and there's an external pressure that pushes inwards. And so those two pressures cancel each other out because they're equal and opposite. And so I'm crushed. However, if I dive down into the ocean, My internal pressure really doesn't change much, but the external pressure would, because I now have the weight of the air above me, or the water above me, in addition to the air. And about 100 meters down or so, the water would actually crush me. Mythbusters actually tested this, and it's pretty gruesome. So, in an atmosphere, the pressure is the weight of the stuff above you. And that's why when you dive down into water, the pressure goes up. Because the further down you dive, the more water you now have above you. If I go up a mountain, the air pressure decreases because I now have less air above me. And so there's less pressure. Now, we like to do things not in terms of pounds per square inch. That's an English unit. We use physics units. The units we use are pascals. A pascal is a Newton per meter squared. The pressure in this room is approximately 1 times 10 to the 5th pascals, give or take 1%, depending upon whether we have a day where we have low pressure or high pressure. Now, in our atmosphere, the pressure only changes by about 1%, not a whole lot, but that 1% is enough to drive the most powerful of storms. And let's examine how powerful that 1% is. Have you ever had a day where you try to open the door and either it flies open or it's just really hard to push open? Well, that's because you have a pressure difference between the inside and the outside. On days where it's windy, usually the door will fly open and be very hard to shut because it's lower pressure outside. On days where it's hot, it may be have a very high pressure outside and a very low pressure inside, and so that door wants to stay shut. So let's examine a day where on the outside the pressure is 1.01 times 10 to the 5th, and on the inside it is 1.00 times 10 to the 5th. And ask yourself, if I have a door that's 2 square meters in area, what is the net force on this door? Because that is how much force I'm going to have to apply to the door in order to be able to open it. So go ahead and do that. So calculate now the air pressure force is the force from air pressure. That's just my fancy way of saying it. So you're calculating the force from the inside pushing out, the outside pushing in, and then calculate the net force, which would give the force that you would have to apply to actually be able to open the door. So go ahead and do that. This is a level 1 problem. Go. Alright, so on the inside, it is 1.00 times 10 to the 5th pascals times 2 meters squared. And a pascal times a square meter is a newton. So this is 2.00 times 10 to the 5th newtons. And the direction, because pressure is every direction, force is not. So the force is going to be basically based on the surface. So it pushes against the surface. Since we have the door, it's going to push outwards. So from the outside, my pressure was 1.01 times 10 to the 5th, which equaled 2.02 times 10 to the 5th newtons. Now in this case, the air from the outside is going to push inwards. I'm going to make it a negative outwards, just because I decided randomly to make outwards the direction of choice. When you have forces, you got to pick the direction. Now, my net force, add these together, and I get minus 0.02 times 10 to the 5th newtons. But that's not a very good way to write it, so I'm going to change it by moving this over 1, 2, and subtracting 2 from this. So that's 2 times 10 to the 3rd newtons out, which would also be plus 2 times 10 to the 3rd newtons inwards. So 2,000 newtons, which is about 400 pounds of force. So I have to apply 400 pounds of force to open the door, which means I'm really going to have to lean to it and use my legs and everything. So it's going to be a really hard door to open. That's only changing it by 1%. So air pressure has a lot of force. A lot of force. So much so that it can break houses. It routinely does. All right, so I kind of hinted at this one. You swim into the deep end. I'm sure most of you have swam in the deep end of a swimming pool at some point in time. What happens? Well, you probably notice your ears feel like they're going to pop because the water is pushing in so much, because the water pressure has gone up. And it's gone up because I now have the weight of the water above me. And so the pressure increases by the amount of the weight of the water for every square meter above me. And so the pressure at some depth equals the pressure at the surface plus density times depth times g, because it's a weight, to get a force. This gets us to a force. Now, if you're dealing with air and you calculate air pressure, now you can only roughly estimate this because the density of air changes as you go upwards. But if you want to do it, say 50 or 100 meters above sea level, you just use a negative depth, and that'll help you calculate the air pressure at some elevation. And so we start off with, usually the surface pressure on the Earth at sea level is 1 times 10 to the 5th pascals. However, if you're on another planet, or if you're, say, diving into a lake in, say, Denver, Colorado, where the surface pressure is probably closer to 7 times 10 to the 4th, then you would use that value here. Now, in this class, most things are going to be done at sea level, and unless we're on another planet, this would be the value at sea level. If we're on another planet, I would probably give you the sea level pressure. So now I put 1.0 times 10 to the 5th pascals here, when in reality it's just the surface pressure here, whatever that surface pressure is. General rule of thumb, about every 10 meters you dive down is 1 extra bar, 1 extra atmosphere, which means an extra 10 to the 5th. So if you dive down 50 meters, that's an extra 5 times 10 to the 5th, so you'd have 6 times 10 to the 5th pascals at 50 meters. The pressure goes up pretty quick in water. All right, calculate the pressure at 240 meters of depth, and then calculate the inwards crushing force on a submarine with the surface area of 0.4 square meters. These are both level 1 problems, so nothing fancy here. And go. All right, hopefully you're finished. For A, pressure at depth equals the surface pressure, 1.0 times 10 to the 5th pascals here because it is the ocean, plus density. Now, this is not a value I expect you to memorize. Oops, I guess I needed to give you that value. I did not. All right, the density of water is 1 times 10 to the 3rd kilograms per cubic meter. The density of air is 1.2 kilograms per cubic meter. Those are not values I expect you to memorize. Those will be on your equation sheet for you Physics 100 students. If you're in a different class, you might want to ask your instructor if those values will be on your test or not. All right, so now that I've included that, go ahead and solve part A and part B. Go. All right, and we're back. So, density depth times G. So 1 times 10 to the 3rd plus, times 240 meters times 10 meters per second squared. This, of course, is kilograms. And this is going to be 2.4 times 10 to the 6th, and times 10 to the 5th, which is 0.1 times 10 to the 6th. So my pressure equals 2.5 times 10 to the 6th pascals. So a lot of pressure, 25 times the pressure in this room. All right, the force equals pressure times area. Now the reason why this is a crushing force is if I have some complicated object like this, the pressure pushes everywhere. Now if I look at the linear force, we're trying to move it side to side, the force here and the force here cancels. So those forces cancel each other out. Now the top force and the bottom force do not cancel each other out, but here we're kind of waving our hands over that. But you can imagine every place here, it's pushing inwards. And so normally those would kind of cancel each other out. But in this case, we're just looking at crushing force, so it's all pushing inwards, so the direction's inwards for everything. So this is how much this submarine's trying to be crushed, because if the submarine goes too far down, that force inwards can no longer be counterbalanced by the force outwards, and it just gets turned into paper mache, even if it's made of metal. So this is 2.5 times 10 to the 6th Pascal times 0.4 meters squared. And then this gives us 1.0 times 10 to the 6th newtons inwards. And inwards is spelled with an N, not an N. Okay. All right. So hopefully that's fairly straightforward so far. More complicated stuff to come. Buoyancy. So now, this is where the rubber meets the road, the buoyancy. Buoyancy is the net pressure force on an object. Now, if I have water that's not moving, which is usually how we'll be calculating buoyancy force, the sides will not contribute to the buoyancy force because they will all cancel out. But on the top, I'm going to have a force pushing downwards, and on the bottom, I'm going to have a force pushing upwards. Now, since the pressure is greater on the bottom than it is on the top, then I'm going to have more force pushing up than I have pushing down. And this difference in pressure, this net force, if you will, is called the buoyancy force. So if you jump in a pool, you get pushed up, that's the buoyancy force. So the buoyancy force is equal to the weight of the fluid that is displaced. Always. The weight of the fluid displaced. So right now I'm displacing air. So if I calculate the weight of the air I'm displacing, I can calculate the buoyancy force that the air in this room exerts on me. Now to do that, I would take the density of the fluid I'm displacing, which is air, 1.2 kilograms per meter cubed, times the volume of air displaced, which is my volume, which is roughly, so we got 2 meters in height, times half a meter times a quarter of a meter, so a quarter of a meter cubed for my volume, so times G. So 1.2 times 0.25 times 10. And that gives me a buoyancy of about 3 newtons. Now 3 newtons is much smaller than my weight of 1,000 newtons. So it's kind of negligible in this case. But if I get on a scale, the scale does not actually measure my true weight. Because the scale only measures how much I get pushed down onto the scale. And since the buoyancy force lifts me up, the scale is off by about 3 newtons. Now, note that the mass of the object is not a dependency for the buoyancy force. So let's do a quick question. See if you read, you probably read some of this, you may be able to get it. All right. Let's imagine 2 objects, a rock and a block of ice that's being held underwater. And both of them have the same volume, 1 cubic meter. Which one has the greater buoyancy force? The 1 cubic meter of rock or the 1 cubic meter of ice. Okay, so look at the equation. And think about what goes into this equation. And give your answer. The correct answer is they're the same. Now, why are they the same? How could they possibly be the same? The rock sinks and the ice floats. How could they possibly be the same? Clearly, would that not indicate that the ice has a greater buoyancy force on it than the rock? Well, let's examine. And when we look at this, we have to look at the net force. We have to look at the big picture. Always have to look at the big picture. Because the little picture usually misleads us. The forces on the object are buoyancy and gravity. And when we add those two together, that's what's going to decide what happens to the object. Not just the buoyancy force, but also the gravity. Well, 1 cubic meter of rock, if it's, say, granite, which is a lighter rock, but rock less, has a density of about 3,000 kilograms per cubic meter. So my 1 cubic meter rock has 3,000 kilograms of mass, which means a weight, it's 30,000 newtons of weight. Oops. For a cubic meter of ice, the density is about 7/10 the density of water, so 700 kilograms per cubic meter. So the mass of the ice is 700 kilograms, which means its weight is 7,000 newtons. 7,000 newtons versus 30,000 newtons. Now each one is going to have a buoyancy force, and the buoyancy force is going to be determined by this equation. This equation. I would make the worst Vanna White ever. Okay. All right, so buoyancy force equals density, which is the density of the fluid displaced, which in this case is water, 1,000 kilograms per cubic meter, times the volume. And since both I specified both are completely submerged, both have a volume of 1 cubic meter times G. And so both of them have the same equation for the buoyancy force, which means that their buoyancy force is 10 to the 4th, or 10,000 newtons upwards. Buoyancy force is usually upwards. If you have a downwards buoyancy force, you're in trouble. Because that would imply that the pressure is greater on top than it is on the bottom. And that doesn't happen very often. So I have 10 to the 4th newtons upwards as my buoyancy force. Now for the rock, I had 3 times 10 to the 4th newtons downwards for gravity. So the net force is 2 times 10 to the 4th newtons downwards, which means it sinks. Now it doesn't quite sink as fast as it would in the air because the buoyancy force slows it down a little bit, but it falls 2/3 as fast. For the ice, I had 7,000 newtons down. By the way, I did this in case you didn't catch it. I had to convert it. I'm going to convert this to a minus up for the ice, plus 10,000 newtons up from the buoyancy, and my net force is 3,000 newtons upwards. So the ice is going to want to rise. So the ice has a net force that's upwards, the rock has a net force that's downwards. That's why the ice floats and the rock sinks. They both have, however, the same buoyancy force, as long as they're completely submerged. Now the really strange thing is, ice usually isn't completely submerged. So if I just let it float and some part of it's out of the water, I no longer displace 1 cubic meter of water. I actually displace less than that. It actually turns out 0.7 cubic meters of water. And so a floating iceberg with the same volume as a sunk rock, the rock will actually displace more water and therefore have a higher buoyancy force on it than the ice, which is floating. As strange as that sounds. All right. Now, so general rule of thumb, if the buoyancy force is less than the gravitational force, it sinks. If the buoyancy force is greater than, it will float up to the surface and slightly above the surface, and if they're equal, it'll just stay wherever it's at, because your net force will be zero. So fish usually have a buoyancy force exactly identical to the gravity force that they can float and do whatever they want. In fact, submarines can change their buoyancy force by adding water or getting rid of water, and that changes their weight, which allows them to change their net force so that they can float or sink. All right. Now let's examine a floating object. Now, an object that's submerged is pretty straightforward. The volume of water displaced is equal to the volume of the object. The buoyancy force is equal to the weight of the fluid displaced, which is the density of the fluid, in this case water, times the volume, times G. But what happens if the object is floating? So I have my ice completely submerged in the water. The net force is upwards. It's going to come up, and it's going to go through the water. Now, as it goes through the water, what happens? There's going to be a change, because it's not just going to fly up and go into outer space. And it's not going to sit completely above the water. It's going to sit in the water. About 70% of it underwater, 30% above the water in this particular case. The question is why? Why is that the case? So let's think about it. As the ice pokes out of the water, it's now displacing, part of it's now displacing air instead of water. And it is if air is so small, we'll ignore it and ignore the buoyancy force from air. So the buoyancy force is going to drop as the ice comes out of the water. Now, since the buoyancy force drops and the gravity stays the same, at some point those forces will cancel each other out. I'll have zero net force. So an object that is floating usually will have zero net force. Now let's think about that. Zero net force. So that means that zero equals the sum of all forces. And I only have two forces, gravity and buoyancy. So let's write that on the board. Floating object, the net force equals zero, which equals the buoyancy force plus the gravity force. Now, let's solve this for the buoyancy force. Now, we can't use this equation here for the buoyancy force yet because we don't know how much volume is displaced. Because some of it is out of the water and some of it is in the water. But we can solve this equation and know that the buoyancy force is equal and opposite to gravity. So when an object is floating, when it's submerged, sorry, let's start with submerged. When an object is submerged, the buoyancy force equals the weight of the fluid displaced. When an object is floating, the buoyancy force still equals the weight of the fluid displaced. We just don't know what the volume is. But it also equals the weight of the object itself. And that will allow us to determine how much volume is going to get displaced. So I can set this equal to mg of the object, cancel out the g's, and get that the volume displaced is going to be the mass of the object divided by the density of the fluid. This is only for a floating object. Now, this is not an equation, it's a solution to a very specific problem, so you will not see this on the equation sheet from the exam, but that's how it works in a nutshell. All right, hopefully that makes a little sense. Buoyancy is a little bit tricky. It really is. And I think I just covered all that, so you can read it. This leads us to Archimedes' principle. A little over 2,000 years ago, there was a man by the name of Archimedes. He was a Greek scientist, very good scientist at the time, the world's best. And he was given the task, the challenge, if you will, by one of the kings, to determine if an object was true gold or fake gold, fool's gold. Everyone at the time knew that fool's gold and real gold had different densities. But what happens if you have a ring that looks like it's made of gold? Is it really gold or not? Now today we use more sophisticated methods. We use electricity or chemical things. So if you take your ring to the pawn shop, they'll stick electrodes to it or do something else to it to figure out what it's actually made out of. But back then they didn't really have that. So they used density. But how do you find the density of some weird, weirdly shaped object? It's kind of hard, isn't it? Well, Archimedes was contemplating this when he decided to take a bath. So he got set in his bath, and notice that as he sat into the bath, the lower he went into the bath, the more the water rose. In other words, he was displacing water. And upon realizing this, he jumped out of the bath, ran down the street, yelling, "Eureka, Eureka, I have found it, I have found it." I like to joke that at some point someone would have pulled Archimedes aside and told him to Eureka's clothes. But what he realized is that there's a way to calculate the mass of an object and a way to calculate the volume of an object. And if you have the mass of an object and the volume, you know the object's density. Because density equals mass over volume. So how do we do that? How do we get the mass and volume of an object to be able to determine its density? Well, the volume. The volume is pretty straightforward. If an object sinks, you take the object, you drop it in water, and see how much the water rises. The volume by which the water rises is the volume of the object. So if you fill a cup all the way to the top with water, and you drop a rock in it, the amount of water that comes out of the cup is the volume of the rock. Okay, so far so good. How do we get the volume, the mass of the object? Well, if an object is floating, so you get an object to float, you put it in a big giant cup so it'll float. And of course you measure the mass of the cup so you're not confused by that. When an object is floating, the buoyancy force equals the weight of the object. Which means that the water displaced, the weight of the water displaced, will be equal to the weight of the object. So you fill up your cup full of water, you put in a paper cup, you put your rock in a paper cup big enough so that the total density of the cup is less than water, so it'll float, and you stick it in the water. And of course you have a really light cup, the rock's much heavier than the cup, so you don't have to worry about the mass of the cup, the paper cup. So you have a big plastic cup or bowl, and you have a little paper cup. And the amount of water that splashes out of the big bowl, because of the paper cup with the rock inside, you measure them, you find the mass of that water, and that's the mass of the object. You do those two experiments, and you've got the density of any object. And so Archimedes was able to determine gold from fool's gold 2,000 years ago without electricity. So that leads to Archimedes' principle. The buoyancy force is equal to the weight of the object if it floats. The amount of water displaced for a floating object is equal to the weight of the floating object. And we saw this from the net force and our understanding of buoyancy. So, before I give you a sample question, let's see this. If you float, you displace water equal to your weight. If you sink, you displace water equal to your volume. So now for a teaser. This one's a really tough teaser. You're on a ship in a lock. That's a basin area that allow you to move up and down from a higher elevation lake to a low elevation lake. You're in a lock with some set amount of water and some water. On board your ship, you have an iron anchor. Iron is 8 times the density of water. You cut the chain off of the iron anchor and you throw the anchor. Now the anchor is initially on the ship, and you throw the anchor overboard. Now here's the question. Is the water level in that lock going to go up, down, or stay the same? So I want you to think about that for a moment. You might even want to pause this while you contemplate it and try to use your knowledge of buoyancy to solve this problem. Go. All right. The correct answer is the water level will decrease. How is that possible? Well, let's examine the water that gets displaced by the anchor. When it's on the ship, it's floating, it's going to displace water equal to its weight. And it has a lot of weight. When I throw it overboard and it sinks, it is now going to displace water equal to its volume. Its volume is much less than its equivalent in weight of water by a factor of 8. And so whatever the volume of the object is,